Hi, my name is Mahmoud Yaman Sirajuddin, and today I'll be presenting assignment 2 for the advanced machine learning course. So let's get started. So this first cell installs the required libraries, so we have nothing to do there. Okay, here we define a seed that we'll be using later for the random states, and here I'm disabling the use of GPUs for TensorFlow, basically because the compute cluster that I'm using here on Azure does not does not have a GPU, and that's why I'm not using it. Okay, to because we can't. Okay, so we have to disable it. Here I have the imports. We don't care about these cells. I'm not using Colab. And here I'm outputting the shape of the data. Okay, so I'm reading the CSV, outputting the shape of the data, and taking the square root of the data shape of the column minus 1. So we have 56,000 rows and 785 columns. If we take a look at the columns, we have a label and then 784 pixels. Okay, so the label represents one of 10 clothing items, and which are these clothing items. Each cell has a value between 0 and 255, which most probably represents a black and white image, okay, or grayscale image. And the images have a dimension of 28 by 28, which is simply 784, or the square root of 784. Okay, here we have these observations. I'm not gonna go over these to keep the video short. And here we're outputting the percentages of each item in the dataset. So as we can see, most of the items have equal percentages. However, some have lower percentages than others. So this could very possibly affect the training, okay, and the accuracy of these items. Okay, here I'm splitting the data into a train, test, validate, split. I'm using the function that I used in the previous assignment. However, I added a stratify boolean flag, which is basically when it's true, it stratifies the splits. Okay, so we're doing this here. And then here we have the label encoder, so we're basically encoding the string labels into integers. Okay, so we create the label encoder and then we fit it. Okay, so we fit transform based on the training data, and we do a fit transform because we want to fit it based on the training data, and then we just transform the validation and the test wise. Okay, now we have the number of classes, which is 10. No, sorry, like it depends. And then we have the one-shot vectors, which is basically just feeding the number of classes and the encoded train vectors to the categorical function. Okay, now we're creating the model. So we have some imports. We have so this function basically creates a model given the description of the layers. Okay, so here we have some type declarations. So the optimizers, we can either use Adam or RMS prop. Okay, here we have a class that represents a layer. We don't have to do this, it's just to keep things nice and tidy. For each layer we have the number of neurons, we have the activation function for each neuron, we have the dropout rate if we want to add a dropout rate, and we have batch norm, okay, which is a boolean flag that indicates whether we want to add batch normalization or not. Okay, this function takes these values. It also takes a learning rate, a constant learning rate. Okay, so here we create the optimizer based on the given value. We use categorical cross entropy if we have one shot, otherwise we use a sparse categorical cross entropy. The model is a sequential that has the input, and then we iterate over the layer specifications and construct the layers by adding a dense layer to our neural network. Okay, and we give it a name. Okay, and then finally we compile the model and return it. So I created this model over here, which is a simple model that has ReLU activations, some batch norm, a dropout, and a softmax. Okay, so here's the model, and then we print the summary. The summary basically shows the number of trainable parameters and the shape of each layer. Okay, so as you can see, the number of trainable parameters, which is the 200,960, is basically this, which is 784. Okay, multiplied by 256 plus 256, which are for the output, which these values are given to the next layer. Okay, I'm not gonna spend a lot of time here. We fit the model, which takes 49 seconds without a GPU, and then we plot the learning curve for this model. Okay, as we can see, the training and validation accuracies converge. Okay, so they are approximately equal, and the training and validation loss also converge, although the loss here is there is a greater difference, but nonetheless they converge. Okay, this indicates that the model is neither over or underfitting, and it's learning. Okay, which is good for a simple model. Now we have the hyperparameter tuning. Okay, so for this we have a function that creates a lot of basically a lot of hidden layers that have the same specifications. Okay, this is basically a helper function. Then we have a build model, which builds the model from the hyperparameters. Okay, so we have exponential decay if there is a learning decay rate. Otherwise, we just use a constant learning rate. Then we have the layer specs, which uses the function that I was talking about previously. Then we create a model using the generated layer specs, and we return a model. Okay, so this function builds the model from the from the hyperparameters. Okay, and then we use a random search MLP. So this function basically mimics the grid random search from sklearn. However, it depends on TensorFlow. Okay, because sklearn and TensorFlow don't mix very well. So we have the following values. So the learning rate is between 10 power minus 4 and 10 power minus 2. We have these values for the other hyperparameters. Of course, they can be modified, and RNG is basically just a random number generator that is provided by MP. Okay, I'm not gonna take a long time with these because I'm already over time. Okay, so here we build the model. Okay, we add the early stops, we iterate over the number, so we basically loop n underscore iter times. Okay, and for each time we build a different model and we fit it and then predict and then get the accuracy and F1 scores. Okay, we update the accuracy and F1 scores for this model, and then if this model beats the current best, we update the best model and then update the leaderboard, which basically has the best of models, and then we return everything at the end. Okay, so I ran this and it took approximately 20 minutes. Okay, now here are the results. So the best model, I'm gonna go down there. Like, I didn't use I printed this, I thought it would be more pretty, but it didn't work out. Okay, so I'm saving the model, and then we have this. So the best model had a, where is it? So it had these the following hyperparameters, and the final accuracy is approximately 91%. Okay, I'm not using Keras tuner, so we don't care about that. So now with the model evaluation, we calculate the required test scores. Okay, we have these values. We're gonna spend a lot of time here, so basically we're just calling the functions, and then we plot the confusion matrix. So the confusion matrix basically tells us that this model works better on some items than others, and I assume it's due to the distribution of the, or actually the percentages of the items in the training data. Okay, so this is it. Thank you for watching, and bye.